understand what the reader problem actually is. Now we will first demonstrate through role play what the problem is and how it can be solved. Let us consider 2 writers and 4 readers. Here Soumita and Sobhusachi will be role playing as writers and Supriyo, Bapun, Sagar and Subhajit will be role playing as readers. So first see the problem.
Writer 1 enters the critical section and write to the shared resource. We will consider here the board as the shared resource. Now reader entered the critical section to read. And reads from the shared resource. Here we can see the data is consistent. Now what if the writer 1 and writer 2 both wants to access the shared resource in the critical section at the same time? Let's see what happens then. First writer 1 enters and writes. In this moment 2 readers comes to read. Now writers 2 also want to access the resource, so he start modifying the resource. In this moment 2 other readers come to read. Here we can see the data is inconsistent here. We will now demonstrate how this problem can be solved using semaphores. To avoid data inconsistency, the writer logs the critical section while accessing it using semaphore and opens it after writing. Here we have used binary semaphores. A binary semaphore is an integer variable that can have 2 values 0 and 1. It is modified only using 2 atomic operations, wait and signal. The wait operation causes the process to wait in a loop till the values of the semaphore becomes positive. When it does, the semaphore value is decremented by 1 and the function returns. The signal operation increments the value of the semaphore by 1 and returns. Here we have used 2 semaphores, mutex and wrt, and 1 variable read count. Mutex used to log the critical section for readers. WRT used to block the writers from entering the critical section, and read count helps to counting the number of readers in the critical section, and it permits the writer to enter when it becomes 0. Mutex is initialized to 1 and WRT is initialized to 1 and read count is initially 0. Read count variable is a shared variable that is accessed by all readers who increment and decrement it while enter or exit from the critical section. Then it must be therefore be protected by a semaphore called mutex to preserve data consistency. WRT is used to protect the primary shared resource, that is the board. Only when WRT is 1, then only writer can write, otherwise he have to wait. WRT 0 means the writing is in progress, so no one can enter the critical section. Now see the writer process. Writer requires the entry to critical section. Then if allowed, that is wait gives a true value, then it enters and perform write. If not allowed, then it keeps on waiting and then he leaves the critical section. Now see the reader process. Reader requires the entry to critical section. If allowed, it increments the read count and checks the read count value is 1 or not. Read count value 1 means This reader is the first reader, so it locks the WRT to prevent writers from modifying the board until all the readers finish reading. It then signals mutex. After reading, it decrements the read count and checks the value is 0 or not. If 0, that means no more reader is inside, so it then signals the WRT so that writer can enter now. Now writer 1 come. Here the WRT is 1, that means she can write, but before she enters the critical section, she changes the WRT from 1 to 0 to prevent others from accessing the board until she finishes writing. After finishes the writing, she changes the WRT from 0 to 1. And leaves the critical section. Now reader 1 comes to read. First he changes the mutex from 1 to 0. Here we assume the door as the mutex. Mutex 1 means door is open and mutex 0 means the door is closed. That means now no other readers can enter the critical section. Now reader 1 increment the read count and checks the read count. If it is 1, then change the WRT from 1 to 0 to prevent writers from modifying the board until all the readers finish reading. Now he changed the mutex from 0 to 1. Now other readers can come and now reader 1 starts reading. Now reader 2 comes. First he changes the mutex from 1 to 0. And increment the read count. Here the read count value is 2, so he does not touch the WRT and change the mutex. And starts reading. Now reader 3 comes. Change the mutex. Increment the read count. Now I can change the mutex. And start reading. Reader 3 completes his reading, so he first changes the mutex. And decrement the read count and checks if it is 0 or not. Here it is not 0, so he changes the mutex again and leaves. Now reader 1 comes and changes the mutex. Decrement the read count. You can change the mutex. And leaves. In this moment, writer 2 comes in the critical section but he sees that the WRT value is 0. That means he have to wait until it's become 1. Now reader 2 also finish his reading and change the mutex. Decrement the read count and check if it is 0 or not. Here it is 0. That means every reader finished reading, and he now sets the WRT value from 0 to 1, thereby signaling that the every reader finished reading and the waiting writers now come and can start writing. Now writer 2 can write in the critical section, and he first changed the WRT to prevent others and writes in the critical section, and after writing he changed the WRT from 0 to 1 and leaves. Now reader 1 comes to read. First he changes the mutex and increment the read count, and read count is 1, so he changed the WRT from 1 to 0. Again change the mutex and start reading. Now reader 4 comes to read and change the mutex. Increment the read count and change the mutex again. And start reading. Here we can see that there is no data inconsistency. Earlier we have seen that in absence of semaphores, when multiple writers attempting to write at the same time, it reaches in the data inconsistency. But now we have seen that the use of semaphore successfully prevents such problems.
Thank you for watching this video.